Hello, good afternoon. We present the poster with the title Aqueous Synthesis of Air-cysteine Stabilizer Copper Sulfide Quantum Dots. Copper quantum dots are a potential alternative to the potentially toxic cadmium quantum dots for different applications, most commonly fluorescence sensing. Copper quantum dots are synthesized in an oil phase and then transferred to an aqueous phase that can facilitate their instability as suspension. In this work, copper sulfide quantum dots were obtained in an aqueous solution using air-cysteine as a stabilizer in Earth atmosphere in ambient temperature. The quantum dots were characterized through these techniques: effects of reactance, molar ratio over stability, crystal size, and fluorescence response are discussed. Broadly, the quantum dots were obtained in three steps. First, LCs was dissolved in ultrapure water and purged with nitrogen. Then the copper chloride is added, leading to its reduction to copper 1, giving a complex that can be dissolved at a slightly acid pH, lending the copper free for reacting with sodium sulfide, giving as product a suspension of stabilized quantum dots. Particularly, these quantum dots are found attractive for fluorescence sensing applications. This work hypothesizes that copper sulfide quantum dots are synthesized in an aqueous solution, where LCs mediates crystal size and stabilizes them, having excellent potential for fluorescence sensing. Well, methods. As mentioned before, LCs and water are purged with nitrogen, then the necessary amount of copper chloride is added and reduced. After the change in pH with sodium hydroxide, sodium sulfide can be added, achieving the copper quantum dots suspension, and these ones can be characterized. As a visual reference, we can see that the copper LCs complex is a white suspension. After changing the pH, the solution becomes translucent, and after adding sodium sulfide, a color change is seen. For the optimization, first, LC's copper molar ratio is changed in these values, and the crystallite size is followed with X-ray diffraction. The molar ratio that gives the best result is then applied to the following experiments, where the copper sulfide ratio is changed, where the lowest crystallite value is accomplished. Also, a fluorescent emission intensity comparison was done. Infrared analysis was used for identifying the typical absorption bands at the quantum dot surface to confirm their functionalization. The central band around 3443 is assigned to the stretching vibration of the LCs, particularly oxygen-hydrogen bonds, as well as adsorbed water. The signals at 1637 and 1373 are assigned to stretching vibrations of the carbonyl and carbon-oxygen bonds, respectively. For LCs, the sulfide-sulfide stretching vibration is seen around 588. Comparing with pure LC's spectra, its characteristic signals, which are the stretching vibrations of the bonds sulfide hydrogen, disappear for the quantum dots, suggesting that the LCs bonds to the quantum dots, as occur in different nanoparticles like silver, lead sulfide, zinc sulfide, and others through thiolate bonds, acting also as a stabilizer for suppressed agglomerates, giving a core shell-like conformation. Hydroxide and carbonyl bonds confer water affinity and stability. The observation suggests that LCs was correctly modified for bonding to the quantum dot surface. The maximum fluorescent emission for the quantum dots is seen as a sharp peak in the red region or area at 652 nanometers, obtained at a wavelength of excitation of 661 nanometers. Having only one signal suggests narrow size distribution of the quantum dots. Excitation spectra only showed one peak, thus attributing continuous energy levels to the quantum dots. Also, the emission and excitation peaks are overlapped, which occurs only in the transitions S0 to S1. To determine the molar radio that enables the smallest crystalline diameter, different molar radius of LCs were used, and crystalline size was followed up with X-ray diffraction. A low LC's molar radius regarding to copper allows a wide crystalline diameter or size, since the quantum dots are not covered enough, allowing agglomeration due to low dispersibility. Moreover, an increased molar radius increases crystalline size, and a high concentration of LCs in suspension increases molecular collisions, promoting cluster formation. An intermediate amount of LCs, that is the molar radius of 3 to 1, allows the lowest crystalline diameter or size. Considering this, the copper sulfide molar radius was varied, and an intermediate molar radius allowed the best result, achieving a crystalline size of 9 nanometers, a value located in the quantum dots diameter range. We can see the fluorescent spectra of functionalized copper sulfide nanoparticles varying the copper sulfur molar radius under the excitation wavelength of 661 nanometers. The emission intensity increases with an increased copper sulfide radius, reaching a maximum at the relation 3 to 1 when the nanoparticle achieves the quantum dot crystalline diameter of 9 nanometers. Nevertheless, the fluorescent intensity decreases markedly with the increase of the copper sulfide radius due to the higher crystalline diameter. From the UV visible spectra of the quantum dots is seen widespread absorption ranging from the UV around 400 nanometers to near infrared, that is around 780 nanometers. This result is similar to copper sulfide nanocrystals obtained in a non-aqueous phase. Also, localized superficial plasmon resonance in the near infrared can be used for determining the stoichiometry in copper sulfide nanoclusters. However, this effect is not observed. This fact indicates that the copper nanocrystals obtained are copper sulfide. The diffractogram of synthesized quantum dots shows good agreement with the UV copper sulfide diffraction pattern, demonstrating that the LCs mediates the synthesis of the desired crystalline phase. In the Raman spectra, it is observed that the peaks that belong to stretching and bending sulfur hydrogen bonds in LCs, that is the black line, disappear in the quantum dots spectra, confirming the LC's bonding to the quantum dot surface. Furthermore, two new vibration modes appear centered around 1450 and 1970 centimeters. These peaks are wide and intense due to the high fluorescence of the quantum dots, a response that dominates over the other signals that should appear, like the stretching modes of the sulfur-hydrogen bond and carbon-sulfur bonds. Here we can see the previously mentioned observations about the Raman spectra. From STEM images, it can be seen that quantum dots have dispersed diameters that comprise values from 9 nanometers to 52 nanometers with spheric shape tendency. Some agglomerations can be seen. Nevertheless, the suspension stays stable without visible precipitates. These observations opposed to the previous ones. But agglomerations can occur for copper nanoparticles due to instability at temperatures over or below 25 degrees Celsius, reaching scattered values of diameter that even can be close to 150 nanometers at 40 degrees, for which better care is suggested when handling STEM samples. All the previously discussed techniques were done in the same laboratory where the temperature is around 25 degrees Celsius. So, in conclusion, water-soluble copper sulfide quantum dots stabilized with LCs were synthesized applying a simple method. These quantum dots had a wide absorption range and showed red fluorescent emission. Infrared observations confirmed LC's binding to the quantum dots surface through disulfide bonds, achieving functionalization and leaving water-soluble functional groups at the exterior of the quantum dots, conferring colloidal stability. The obtained crystalline phase and crystalline diameter were confirmed with X-ray diffraction observations, supporting the advantage of using LCs to mediate copper sulfide nanocrystal growing. Also, stoichiometry is demonstrated with the absence of localized superficial plasmon resonances. The fluorescence of the synthesized quantum dots seen as overlapped emission and excitation peaks, which suggests a narrow size distribution and only one electronic transition. This work finally opens possibilities for its use as a fluorescence sensing material for different analytes. Thanks for your attention.